Fellow calculus students, this lesson is on continuity and differentiability. Let's begin with a definition of continuity that we've already discussed, which is our third statement. A function is continuous at x equals a if the limit as x approaches a equals f of a itself. In other words, the graph is getting closer and closer to the actual y-coordinate, creating a continuous flow through that y-coordinate. Now we introduce two new terms. F is right continuous at x equals a if the same thing is true but only for the right-sided limit. So as x approaches a from the right of this function, we must get closer to the actual y-coordinate f of a. F is left continuous at x equals a if the limit as x approaches a from the left of the function is equal to that y-coordinate f of a. This example ought to clear this up. Consider the image of the function f below. Complete the table that follows wherever possible. Let's do one row at a time. Let's focus on when a is -5, and a is our input coordinate. So we're looking at -5 for the x. Now as x approaches a from the right, we get closer and closer to an output coordinate of 2. Remember, a limit is only concerned with what we are approaching, not with what occurs when x actually is -5. Now we do a limit as x approaches a from the left, but notice there's no graph left of x equals -5, so we simply say that this limit is not possible. So the two-sided limit we would say does not exist. F of a is what is the actual y-coordinate when x is -5. That's where this solid point is, and that y-coordinate is 3. So can this function be continuous at x equals -5? Well, the answer is no, because to be continuous at a location, we need to have a two-sided limit that exists and is the same thing as the y-coordinate. But here we have a two-sided limit that doesn't exist, therefore we say no. What about right continuous? So we look at the result of the limit as x approaches a from the right, which is 2. Is that the same thing as the y-coordinate? The answer is no. So we say no here. And then is the function left continuous at x equals a? Well, the left limit was not even possible. So there's no way that the left limit can be equal to the y-coordinate. So we'll say not possible, or we can simply say no. Let's focus now at the x-coordinate -1. The limit as x approaches -1 from the right. So we imagine points on this curve getting closer to -1 from the right, and we can see that we are approaching a height of 6. So our right-sided limit is 6. And now let's approach -1 from the left. And as we do this, the graph gets closer and closer to a height of 4. Now, because these two one-sided limits do not match, the two-sided limit does not exist. We do have a jump discontinuity here. Now, what is f of -1? Well, that's where the actual point is. And so this function actually outputs a 1 when x is -1. So now we get to say, is f continuous at x equals a? Well, the two-sided limit does not exist. So this statement up here can't be true. So we'll say no. Is f right continuous? Well, to be right continuous, we need the right-sided limit and the y-coordinate to match, which they don't. So we'll say no. Is f left continuous? We would need the left limit and the y-coordinate to match, which they don't. So we'll say no for this as well. Okay, let's move to x equals 3. As x approaches 3 from the right, the outputs are getting closer to an output of 5. As we approach 3 from the left, we get outputs that are getting closer and closer to a height of 1. So the two-sided limit, again, does not exist. This is another jump discontinuity. The value of f of 3 is indicated by the y-coordinate of the solid point, which is 5. And now we can ask questions about continuity. Are we two-sided continuous? No, because the two-sided limit does not exist. Are we right continuous? Well, the right-side limit is 5, and the y-coordinate is 5. So we get to say yes, because this limit and this y-coordinate match. Visually, it just means that as we approach 3 from the right, we are approaching a solid point. So we say we are right continuous at that solid point, or continuous from the right. Are we left continuous? Well, the left limit and the y-coordinate do not match, so the answer is no. Okay, now we look to an x-coordinate of 5. As x approaches 5 from the right, we are approaching an implied solid point right here, whose output is 4. So the y-coordinates approach 4 as x approaches 5 from the right. Also true, as x approaches 5 from the left, the outputs get closer and closer to 4. The left and right limits are the same, so the two-sided limit is also 4. And when you plug 5 into this function, you get an output of 4. So the two-sided limit and the function value match. So the function is continuous at x equals 5, which visually means that you can draw through that point without needing to lift your pencil. If x is continuous for an x value, it will also be right and left continuous there, because the two-sided limit needs to match both of the one-sided limits, which match the y-coordinate. Shifting to x equals 7, as we approach 7 from the right, our outputs get closer and closer to a height of 3. That's also true as we approach from the left. Therefore, the two-sided limit is also 3. However, f of 7 is way up here with an output of 6. So is the graph continuous at x equals 7, or the two-sided limit and the output do not match? So we say no. In fact, there is a removable discontinuity here. Therefore, it cannot be left or right continuous either, because both of these limits match the two-sided limit, and none of it matches the 6. Now let's focus on x equals 9. The right-sided limit, there is no graph to the right of 9, so we'll say that this limit is not possible. However, the left-sided limit, as we get closer and closer to 9 from the left, the outputs get closer to an output of 4. The two-sided limit we'll say does not exist, and the output of the function is also 4, because that's where the solid dot is. So we cannot say that overall the function is continuous at x equals a, because it's not two-sided continuous. We're going to say that it's not even possible to be right continuous, because the function does not exist to the right of 9. And is the function left continuous with the left limit and the y-coordinate match? So the answer here is yes. In other words, as we approach 9 from the left, we approach a solid dot. Okay, let's go to the next page. A function is continuous on an interval if it is continuous at every x value in that interval, including left or right continuous as appropriate for endpoints of the interval that are included. Draw functions that are continuous on the indicated intervals. So you want to draw a function that is continuous on the half open, half closed interval. You say closed on this side because of the inclusion of -2, but open on this side because of the exclusion of 3. So when x is -2, we want a solid point somewhere. And then when x is 3, we want a hollow point somewhere. And then connect these points with a function in a continuous manner. Make sure it's a function, so no doing something like this because this fails the vertical line test. And it has to be continuous all the way across, so I can't do this because there's a discontinuity. So I have to connect these points in such a way that I pass the vertical line test and never lift my pencil. Something simple like that, or more erratic like that, it doesn't matter. Let's go with something rather simple. Now, whether or not there's a solid dot when x is 3 is irrelevant. So if I put a dot here at 3, -1, we would still say that this function is only continuous on -2 inclusive up to 3 exclusive, because we are right continuous at the left endpoint, but we are not left continuous at the right endpoint. Now, another consideration is that we maybe have an asymptote at 3. So instead of approaching a hollow point, it could be that we have a graph like this that approaches a vertical asymptote. And so we would say that this function is continuous from -2 inclusive up to 3 exclusive. Now we want a function g that's continuous from -1 up to infinity, -1 excluded. So I'll start at a hollow point and then just draw something that's continuous off to the right. Or we could have made an asymptote at -1 and then draw something that's continuous to the right of that asymptote. For my notes, I'll stick with this example. Now we want to draw a function h that is continuous from -infinity up to pi inclusive. Pi is about 3.14, so a little bit past 3. We need to have a solid point, maybe here at pi 1. And then off to the left, we need the graph to be continuous and then approach that solid point and then go forever to the left. An asymptote at pi would not be possible because we need pi to be included. Now here's a list of function types that are continuous on their domains. Polynomials. For example, coefficients can be any real number, so -1 and 0.5, but the x terms have to have powers that are whole numbers, so 0, 1, 2, 3, etc. And polynomials are always continuous on the entire number line, so they're continuous for every value of x. Now rational functions, which are fractions of polynomials, can have discontinuities wherever the denominator is 0. So they're continuous wherever the denominator is non-zero. For example, consider x plus 1 over x minus 3. X equals 3 is forbidden because that causes division by 0. So this function is a rational function that is continuous everywhere except 3. So we'll say it's continuous on -infinity up to 3 union 3 up to infinity. And notice my 3's are not included because of these parentheses. Power functions, x to the p. Depending on p, you have different domains, but whatever the domain is, power functions will be continuous on their domains. To illustrate, x to the 1/2, that means square root of x, has a domain of 0 to infinity. You cannot take the square root of a negative number. So this function is continuous on that domain from 0 inclusive up to infinity. However, x to the 1/3, which is the cube root of x. Now you can cube root a negative number. For example, cube root of -8 is -2, because -2 cubed does give you -8. So an odd root of x is defined for any value of x. So this function will be continuous on the entire number line. And if you have a negative power, such as x to the -1/2, that means 1 over the square root of x. Well, this one, x has to be non-negative, but it also can't be 0 because you would have division by 0. So this one has a more restrictive domain, and that domain is 0 to infinity, exclusive of 0, and this is the interval for which this function will be continuous. Exponential functions, where the base is positive but not 1, they're growing exponentials if the base is more than 1, but decaying exponentials if the base is between 0 and 1, but these functions are continuous for any value x, continuous on the entire number line. Logarithmic functions, log base b of x, b must be positive but not 1, and x must be strictly positive for the logarithm to be defined. So the domain is 0 exclusive to infinity, and these functions will be continuous on that domain. And trig and inverse trig functions, I encourage you to graph. Sine of x is continuous everywhere, so is cosine of x. Tangent of x has many discontinuities, but wherever the function is defined, the function is continuous. In other words, all these pieces are continuous separately. Secant of x, cosecant of x, and cotangent of x are also similarly continuous wherever the functions are defined. And inverse trig, arcsine, arccosine, arctangent, arccotangent, arcsecant, and arccosecant are all continuous where they are defined. Now, if you have two functions f and g that are continuous at x equals a, then if you add or subtract them, you still have a continuous function at a. If you multiply them, still continuous. If you multiply the function by a constant k, still continuous at x equals a. If you raise a continuous function to a whole number power, the result will still be continuous at x equals a. If you divide two continuous functions, the result will be continuous provided g of a is non-zero. So x plus 1 is continuous, x minus 3 is continuous. If you divide them, you get continuity provided the denominator is non-zero. So we had continuity on this interval, union this interval. And if you do a composition, you plug a function into a function, the result will be continuous at x equals a, provided that f itself is continuous at g of a. I don't want to go too far into the weeds on this one. Let's just do an example or two. I'm going to do a composition of x squared minus 4 into the square root of x function. Now the interior function is continuous everywhere, but when I plug it into the square root function, we're going to have some domain restrictions. You can only square root non-negative numbers. So we need this argument x squared minus a to be bigger or equal to 0. Well, if you graph x squared minus 4, it's a parabola that's been shifted down 4 units. It does cross the x-axis at negative 2 and 2. So between negative 2 and 2, we have negative outputs, which we cannot allow because I cannot square root a negative number. So this tells me that x must be bigger or equal to 2, or the x must be less than or equal to negative 2. In other words, this function, with the radical, will be continuous on the interval from negative infinity up to negative 2 inclusive, union 2 inclusive up to infinity. Okay, let's go to the next page. Now, a function is differentiable at x equals c if it is continuous at x equals c and f prime of c exists. F prime of c stands for the slope of the line that is tangent to the curve at x equals c. And to say that f prime of c exists means that the slope of that line must be a unique finite value. So in other words, at x equals c, a unique tangent line is possible with a defined slope. Now we're about to see that there are two general cases where we're going to have a function that's continuous but not differentiable. And they're going to be sharp corners, such as right here. Drawing a tangent line at a sharp corner won't be possible. And then locations on the curve where the tangent line would be vertical, because vertical lines do not have defined slopes. Now, a function is differentiable on an open interval from a to b if it is differentiable at every x value in that interval. We say that the function is smooth on that interval. And we will adopt the convention that a function cannot be differentiable at an included endpoint. Okay, given the function below, identify all x values where the function is discontinuous. Okay, as we draw this function, I have to lift my pencil right here to go around that missing point. I have to lift my pencil again to do the jump. I have to lift my pencil again to get around this vertical asymptote. And then I can draw the rest of the function without lifting my pencil. So I found discontinuities at these three locations. So negative 6, negative 4, and 1. In particular, we had a removable discontinuity at negative 6, a jump discontinuity at negative 4, and an infinite discontinuity at x equals 1. Now identify all x values where the function is not differentiable. Well, anything in this list will also be in the next list, because for a function to be differentiable, it must first be continuous. In addition to that, the function will not be differentiable at this sharp corner or at this location where the tangent line would be vertical. So in x is 3, we have a sharp corner at which no tangent line can be drawn because the function instantaneously changes from one slope to another. And then at this location, we have a vertical tangent line, and vertical lines have undefined slopes. So we add to our list both 3 and 5. Everywhere else, we say that function is smooth. Identify all intervals on which the function is continuous. So this first piece, up to this missing point, the function is continuous. So that's negative infinity up to negative 6, exclusive of negative 6. The function's continuous on this interval, and at the right endpoint, we're left continuous. So we end on a solid point. So we go from negative 6 exclusive up to negative 4 inclusive. This portion here is continuous. So that's from negative 4 exclusive up to 1 exclusive because of the vertical tangent. And then the remaining portion is also continuous, including being right continuous at the left endpoint. So we are also continuous from 1 inclusive up to infinity. And it's better to use commas to separate these instead of the union signs. Now identify all open intervals, and notice for differentiability, we're going to insist that we only give open intervals. That means exclude both endpoints on which the function is differentiable or smooth. So you have one interval, negative infinity to negative 6. Then we're smooth on this open interval, that's negative 6 to negative 4. Then we're smooth for this piece from negative 4 to 1. We're smooth between 1 and 3, smooth again between 3 and 5, and then finally smooth from 5 to infinity. Now note that polynomial, rational, exponential, logarithmic, trig, and inverse trig functions are all differentiable on open interval versions of their domains. Now notice in this list I don't mention power functions. Power functions can be a little bit tricky. Here's an example of a power function, y equals x to the 1/3. Identify where this function is continuous and differentiable. Use technology to graph the function to confirm. X to the 1/3 is the same thing as the cube root of x, so we're doing an odd root of x. You can odd root positive, 0, or negative. So this function is continuous on the entire number line. However, let's find the derivative. Y prime, we'll use the power rule. The 1/3 will drop down. X to the new power would be negative 2/3. Well, if I rewrite that negative power puts that x in the denominator with the 2/3 power, which can be rewritten as the cube root of x squared. Now, positive x's and negative x's are still allowed here, but we do get one restriction of x no longer allowed. X cannot be 0 because it's now in a denominator, and that would cause division by 0. So y prime does not exist at x equals 0. So the function y is not differentiable at x equals 0. So y is differentiable everywhere else. So from negative infinity up to 0, or on the interval from 0 to infinity, parentheses on both zeros. Here's a graph of x to the 1/3. It's continuous everywhere, but is not differentiable at x equals 0 because at x equals 0, the tangent line would be vertical. Here's a graph of x to the 2/3. Its derivative will also be undefined at 0, and the reason this time is because of a sharp corner. If my power of 4/3 is more than 1, this function will be differentiable at x equals 0. We'll have a smooth transition through the origin. Here's x to the 1/2, or the square root of x. It is continuous, including at the endpoint 0, but it is not differentiable at 0 because 0 cannot be plugged into the derivative because our slopes are approaching a vertical slope by the time we get to the origin. Okay, let's go to the next page. Graph each pair of related functions below. Identify all open intervals where each function is differentiable. Okay, the first case, y equals x. This is a line slope 1 going through the origin. This function is differentiable everywhere. The tangent line exists and has a slope of 1 no matter which x you pick. So it's differentiable on negative infinity to infinity. Now we're going to compare this graph to the graph of absolute value of x. The effect of finding the absolute value of a function is that anywhere the outputs are negative, those outputs will now become positive. So this portion of y equals x, which has negative outputs, will reflect around the x-axis because the outputs will now become positive due to the absolute value. So here's the graph of absolute value of x. It does produce a sharp corner at the origin, so this function will only be differentiable for every x value except x equals 0. So differentiable from negative infinity to 0, open interval, or 0 to infinity, open interval. You cannot do a tangent line at a sharp corner. Now y equals 1 minus x squared. This graph will be x squared reflected around the x-axis because of the negative, and then shifted up 1. It's upside down parabola, crossing the x-axis at 1 and negative 1. This is smooth everywhere. At any point on this curve, you can draw a tangent line with a defined slope. So also differentiable on negative infinity to infinity. Now when you take the absolute value of this function, these portions of the parabola that are below the x-axis will reflect around the x-axis and be above. This will cause two sharp corners, making a function that's only differentiable from negative infinity to negative 1, negative 1 to 1, and 1 to infinity, all open intervals. And this third example is a polynomial in factored form. If you plug in 0, you'll get 1 back. Negative 1 will be an x-intercept, and positive 1 will be an x-intercept. And this square on this factor, which gave us x-intercept 1, indicates the function will not cross the x-axis there. The graph of this polynomial will look something like this, which is differentiable everywhere. In fact, all three of these examples are polynomials, and polynomials are differentiable and continuous everywhere. But now when I take the absolute value of this function, this portion here that's below the x-axis will reflect around the x-axis, giving us this graph. Now this graph only has one sharp corner. At this x-intercept, the graph is flat and smooth. It has a tangent line whose slope is 0. So at the orange point, the function is differentiable. Only at the red point is it not. So this function will be differentiable from negative infinity up to negative 1, and then from 1 to infinity. Here with technology is a graph of our third example. And if I put absolute value bars around this, we can see a function with only one sharp corner, but otherwise differentiable everywhere. Okay, let's go to the next page. Find values of a and b so that the piecewise function below is both continuous and differentiable for all real numbers. So we don't know a and b, but they're unspecified constants. This first piece of the piecewise function is a polynomial, so it will be continuous and smooth everywhere it's defined. And this second piece is also a polynomial, a line to be specific, also continuous and smooth wherever it's defined. So the only x value for which we have the risk for losing continuity and differentiability is at the x value of transition, at x equals 2. Now we want the two pieces to join in such a way that we don't create a sharp corner when x equals 2, which means that we want the derivatives for the respective pieces to match when x is 2. Let's call the first piece f sub 1 and the second piece f sub 2. Now we want to be true is that if you find the derivative of the first piece and then you plug in 2, that we will get the same thing as when you do the derivative of the second piece and also plug in 2. This will ensure that the slopes of the tangent lines match at x equals 2, creating a smooth transition from one function to the next, not a sharp corner. So let's find what these derivatives are. f1 prime of x is equal to, use the power rule, 3 times the a, treat a like a constant, and then x power 1 less, down to 2. And the derivative of f2, this is a line, its derivative is simply its slope. Now this derivative is non-constant. We do want to plug a 2 in for the x. This derivative is constant, but if there were an x here, we'd want to plug 2 into that as well. f1 prime of 2 is equal to 3a times 2 squared. We want that to be equal to f2 prime of 2, which is just negative 2. This gives me an equation for which I can solve for a. 2 squared is 4 times 3 is 12. So 12a equals negative 2, and divide by 12, and we get negative 1/6. A needs to be negative 1/6 to ensure differentiability at x equals 2. So we also have to ensure continuity at x equals 2. So we want f1 of 2 to be equal to f2 of 2. We want the outputs to match. So plug 2 into f1 gives me a times 2 cubed. We want that to be equal to, and now plug 2 into f2. So negative 2 times 2 plus b. Furthermore, we know that a has to be negative 1/6. So we get negative 1/6 times 8, that's negative 4/3. This will be equal to negative 4 plus b, and I can now solve for b. So add 4 to the other side. Adding 4 is equivalent to adding 12/3, so I have a common denominator. So I'm going to get 8/3 for my b value. Let's confirm this with technology. So I'm going to type in y equals ax cubed, add a slider for a, and we get different graphs depending on what a is. Now let's crop it for x being less than 2. So we only see a portion of this cubic graph. The second portion is y equals negative 2x plus b. So add a slider for b. Crop this for x being bigger than or equal to 2. And we get different values as we change b. Changing b just changes the vertical shift. So we want to find a b value so that the overall function is continuous, but we also want it to be differentiable. We don't want a sharp corner. We've discovered that we need a to be negative 1/6 and b to be 8/3. With these choices of a and b, we can see that we have not only a continuous function, but a smooth function. We transition from red to blue without producing a sharp corner. So even at the point of transition, we could draw a tangent line and find its slope. Okay, let's go to the next page. The intermediate value theorem. Suppose a function f is continuous on a closed interval, a to b. When I say closed, it means both endpoints are included. Furthermore, f of a and f of b are not the same value, and k is between f of a and f of b. Then there exists some c in the open interval from a to b such that f of c equals k. Now what does this mean? Let's say we have two different x coordinates, a less than b. The outputs of the function are different. Let's give a this output and b a different output. And the function must be continuous and must be a function. So no doing this is not a function. No doing this function is not continuous on the closed interval. But you could do something simple like that or something a little more interesting like this. But you must connect the 2 points without lifting your pencil. If that's the case, then if you pick some k that's in between f of a and f of b, so think of k as an output. So here's y equals k, and it's between f of a and f of b. Then it must be true that in order to connect these two black points with a continuous function, that you're going to have to cross this orange line at least once. You could get it over with early and then never touch it again. You could cross it only at the very last minute, Or maybe you can cross it multiple times. But what is guaranteed is that no matter how you connect these dots, you're going to have to cross the orange line. So there exists some c that's in between a and b, such that this k value is also f of c. It's the point you get when you plug c into this function. This does not say that there exists only one c. It says there exists a c. This should be interpreted as there exists at least one c. Now demonstrate why the function must be continuous on the closed interval for the intermediate value theorem, or IVT, to be true. What if the function is continuous on a half-open interval, such as this, but maybe f of b is up here? But in this case, you could find a k value that's between f of a and f of b, but which never intersects the function. This is why continuous on the closed interval is a requirement for the intermediate value theorem to apply. Now this is a useful theorem for a few reasons. I'll give you just one. Find two intervals with integer endpoints and with a width of 1 in which the function below must have roots. Confirm with technology. Now the word root just means x-intercept in this case. We're going to do this by making a table of points. If I plug negative 2 into this function, negative 2 to the fourth, which is 16, and then plus 4 is 20, minus 1, we get 19. Let's go the next integer up from negative 2, plug in negative 1. Negative 1 to the fourth is positive 1, and then add 2 is 3, and then minus 1 is 2. Now f of 0. Plug in 0, we get negative 1. Notice we went from a positive to a negative y, and 0 is between positive and negative numbers. So it must be true that for some x between negative 1 and 0, there's an x-intercept, because this function's a polynomial, and all polynomials are continuous. So plotting these last 2 points, knowing that we have to connect the dots in a continuous way, means we must cross at least once between x equals negative 1 and x equals 0. Now we are asked to find two such intervals, so let's continue finding y-coordinates. Plug 1 into the function. 1 to the fourth is 1 minus 2 minus 1 gives us negative 2, so we're still negative. And now let's plug in 2. 2 to the fourth is 16, minus 4 is 12, minus 1 is 11. So once again, we have a transition from a negative to a positive y. You made a point way up here somewhere, meaning there must be another x-intercept between 1 and 2. So we know there's at least one x-intercept in the interval from x equals negative 1 to 0, and there's at least one x-intercept in the interval from x equals 1 to 2. Now, a fourth-degree polynomial may have up to 4 x-intercepts. And when I graph the function with technology, we see that in the end there are only 2 x-intercepts, and the first one is in fact between negative 1 and 0, and the second one is in fact between 1 and 2. Okay, let's go to the next page. The mean value theorem, MVT. Suppose a function f is continuous on a closed interval and differentiable on the corresponding open interval. Then there exists some c in the open interval, so between a and b, such that f prime of c is equal to f of b minus f of a over b minus a. So once again, we're starting with a function that is continuous on a closed interval and differentiable on the open interval. So for all the interior points, we can draw a tangent line and find its slope. Now this expression right here, f of b minus f of a over b minus a, that's the average rate of change of the function between x equals a and x equals b. It's the slope of this secant line. Now what the mean value theorem is saying is that for some interior point, there's going to be a point where the tangent line has the same slope, and the slope of the tangent line is given by f prime of some number. We'll say c, and that value c is somewhere between a and b. And maybe there's more than one. If I draw this curve that's differentiable between a and b, I can see that there are 2 different points on the curve where the tangent line would be parallel to the orange secant line. So we'd have a c1 and a c2. So this theorem says there exists a c that should be interpreted as there exists at least one c. Now demonstrate why the function must be differentiable on the open interval for the mean value theorem to be true. The question is it possible to draw a continuous function that's not differentiable where we will not be able to find a value c where the tangent line is parallel? You can cause an issue by allowing for sharp corners. For example, what if I do a function, something like this? It is continuous, but it is not differentiable because of the sharp corner right here. In a case like this, there is no c in the interval from a to b, where the tangent line would have a slope, so f prime of c, that equals the slope of that orange secant line. So for the mean value theorem to be applicable, we need the function to be continuous on the closed interval and differentiable on the open interval. Find a value of c guaranteed by the mean value theorem for the function and interval below. Confirm with technology. So this function, the square root of x, has a shape something like this. This function is continuous on this closed interval, 1 to 4, and differentiable on the open interval from 1 to 4. So the mean value theorem applies. 2 points on this curve are 1, 1, and 4, 2. Let's begin by finding the slope of the secant line. So f of 4 minus f of 1 over 4 minus 1. So the difference of the y-coordinates over the difference of the x-coordinates, and we get 1/3. Visually, we know that there will be some c somewhere in between 1 and 4 where the tangent line slope would be the same. So we set the derivative of this function equal to the slope of the secant line, which is a third. And then we'll solve for x. Well, the derivative of square root of x, that's x to the 1/2. Use the power rule, 1/2 x to the negative 1/2, and then rewrite as a radical. 1 over 2 square roots of x is the derivative, and we want that to be 1/3. We'll invert both sides, divide by 2, and then square both sides to cancel the radical, and we get x must be 9/4. 9/4 is between 1 and 4, and it is the c value guaranteed by the mean value theorem. Looking at technology, here's our function. We have a point at 1, f of 1, a point at 4, comma, f of 4. The slope is f of 4 minus f of 1 over 4 minus 1, in fraction form, 1/3. Let's make the equation of the secant line, and let's use the first point. So y minus the y-coordinate is equal to this m times x minus the x-coordinate. Let's create a slider for c, and now let's graph a point at c, comma, f of c that I can move around using my slider. Restrict c between 1 and 4, and let's graph the tangent line. Y minus f of c, which is the y-coordinate of the red point, is equal to, and then we can just type in f prime of c, that will be the slope of the tangent line, times x minus c. And now we have a red tangent line. And as you vary c, you can see how the slope of that red tangent line changes. We want to find the value of c where the red and orange lines are parallel. And our math tells us that that value of c should be 9/4, or 2.25. And our image confirms we have found the point of tangency where the slope of the tangent line equals the slope of the secant line. Okay, and this concludes our lesson on continuity and differentiability.